Today we're pulling back the curtain on the hidden digital brains that are quietly running so much of our modern world, artificial neural networks. We're going to break down how they work, how they learn, and seriously, why they are completely changing everything.
So, just think about this for a second. Unlocking your phone with just a glance, your bank sending you a text about a weird transaction, or asking a chatbot to write a poem for you. I mean, what's the one thing that connects all these totally different technologies?
Well, the answer isn't just, faster computers or more data. It all comes down to a single, incredibly powerful idea that is completely changing the game.
That's right. The secret sauce is an architecture that is literally inspired by the most complex object we know of in the universe, our own brain. We've basically been trying to build a digital version of those billions of interconnected neurons that let us think and learn and see the world around us.
So that leads us to the big question. How in the world do you take the, squishy biological stuff inside our heads and translate that into code that can actually learn and make decisions on its own?
Well, this is where something called an artificial neural network, or ANN, comes in. At its heart, it's a web of interconnected digital neurons. But instead of passing around biological signals, they're passing numbers back and forth. This simple setup lets them chew through massive amounts of data, find patterns you'd never see, and ultimately learn from experience.
And the basic blueprint is surprisingly simple. Think of it in 3 parts. First, you've got the input layer. This is like the network's eyes and ears. It takes in all the raw data. Then in the middle, you have one or more hidden layers. This is where all the magic happens, where the real thinking and pattern finding goes on. And finally, you have the output layer, which gives you the final answer. Yes, no, that's a picture of a cat.
Okay, so having a structure that looks like a brain is cool and all, but how does it actually, learn anything? It's not about writing a bunch of rules. It's about letting it figure things out for itself.
The learning process is basically a super fast, sophisticated game of trial and error. First, data goes in. As that data moves from neuron to neuron, it gets multiplied by a weight, which is just a number that represents how strong or important that connection is. Eventually, the network makes a guess. And here's the key part. It compares its guess to the actual right answer. If it's wrong, it sends a signal backwards through the whole network to adjust all of those weights, just a tiny bit. It's basically telling itself, whoops, that guess was wrong. Let's make the connections that led to it a little weaker so we don't make that mistake again.
So let's say you're showing it thousands of animal pictures. You show it a picture of a cat, and the network confidently says, dog. Now, this isn't a failure. This moment, right here, is where the learning actually begins.
That gap between its prediction, dog, and the reality, cat, is the error. And that error is the single most valuable piece of information it can get. It's the signal to go back, tweak its internal wiring, and get a little bit smarter. It literally learns by being wrong over and over and over again, thousands, even millions of times.
Okay, so that's the theory. Kind of abstract, right? Let's make this way more concrete with a super simple, practical example. Imagine we're building a tiny little neural network to do one thing and one thing only: predict if a student will pass or fail a test. And we're only going to give it one piece of information: how many hours they studied.
So we train our model on some examples, and then we ask it a new question. What about a student who studied for 3.5 hours? The network does its calculations and spits out a single number, 0.45.
So what does 0.45 even mean? It's not a clear pass or fail, right? Well, in our little model, we decided that 0 means definitely fail and 1 means definitely pass. Since 0.45 is much closer to 0 than it is to 1, the network is predicting that the student will probably fail. You see, it's not just giving a yes or no answer, it's giving us a calculated probability based on what it's learned.
Now, what we've seen so far is a very, very basic network, but the real power comes from specialized versions that are designed for specific tasks. Think of it as a whole family of different kinds of digital brains.
First up, you've got the Convolutional Neural Network, or CNN. This is basically the visual cortex of the AI world. These things are absolute masters at understanding pixels and finding patterns in images. And this is why they are literally everywhere. The face recognition that unlocks your phone, that's a CNN. AI that can spot tumors in medical scans, sometimes better than a human doctor, a CNN. The eyes of a self-driving car that can tell the difference between a pedestrian and a lamppost, you guessed it, CNNs.
Next, let's meet the RNN, or Recurrent Neural Network.
This one's special skill is memory. It's designed to understand sequential data, where the order of things is everything. I mean, think about it. In a sentence, the order of the words completely changes the meaning. That's why RNNs are the power behind things like language translation, the brains in Siri and Alexa that actually understand what you're saying, and even the complex models that try to predict where stock prices are going to go next.
So let's just zoom out for a second. The impact here is just staggering. We're talking about healthcare systems that can predict disease, financial networks stopping fraud in milliseconds, and recommendation engines that know what you want before you do. These are not small improvements. These digital brains are fundamentally changing how entire industries operate.
But all of this incredible power isn't without its own challenges. There are some really big pitfalls that we absolutely have to be aware of.
The good stuff is obvious. They can find incredibly complex patterns and be amazingly accurate. But the downsides are huge. They need enormous amounts of data, they cost a fortune in computing power to train, and maybe most importantly, they often operate as a black box. We can see the data that goes in, and we can see the answer that comes out, but understanding the exact reasoning for why it made that choice can be incredibly difficult, if not impossible. It's such a big challenge that a whole field called explainable AI has popped up just to try and peek inside.
And this really leaves us with a critical question for all of us. As these powerful but often opaque digital brains start making more and more decisions about our health, our finances, and our safety, how do we build systems of trust and accountability around them? That's the challenge we all face as this technology continues to grow at a breathtaking pace.